So we'll continue our discussion on gravity. And in the previous lecture, we had seen the gravitational field that was created by continuously shaped objects like a rod and a disk. And today we'll be looking at the gravitational field and gravitational potential created from a spherical shell and a solid sphere. Okay. So, just to remind everybody, we have been calculating this gravitational field intensity at a given point where we will keep our test mass, and this gravitational field is coming from a source mass. And like I had mentioned, today we'll be looking at that source mass being a spherical shell or a solid sphere. Okay, and this is our expression for calculating the intensity of the gravitational field, which is given as the mass times the gravitational constant divided by r square, which is the distance of separation between the source mass and where we'll keep our test mass. Okay. Again, the negative sign represents the force being an attractive force in the direction of this unit vector r from your source position. Okay. Going to find the gravitational field inside and outside the spherical shell. So now we'll have two regions where we'll have to consider in case of a spherical shell, because it's hollow from the inside. And similarly, for the sphere as well, which is a solid sphere, we have to look at different regions where we might want to find the gravitational field. We'll also look at the gravitational potential inside and outside the spherical shell. Okay. The idea for spherical shell again is that we want to consider a small mass element. We'll consider a small slice that is shown here, which is AB. Okay, so this spherical shell we are seeing from a top view here, so it is appearing to us as a two-dimensional figure, but you can understand that it is a three-dimensional object. And the capital R is the radius of this spherical shell. Okay, and since it's a spherical shell, it is hollow on the inside. So whatever you're seeing, this green region here, that is the basically the width of this shell, and it's we are saying that it is a very thin spherical shell. Okay, now again we have to define the mass, so let capital M be the total mass of this thin spherical shell. Okay, so we will first take a slice, and this slice that we will get AB will look like a hollow ring, right? And it will be a two-dimensional hollow ring, right? And from our definition, what we want to do is we want to first find and ask ourselves that from this small mass element here, which is this slice that is shown here, what is the gravity that this small mass element creates at a certain point P, okay, along this axis. All right, and then we can define, let R be the distance from the center of the spherical shell, okay, and let S be the distance from this mass element here on the top to your point P, okay, and capital R is the radius. Okay, so we can define some angles as well. Theta is the angle between this capital R and small r, and alpha is the angle between this distance S and R. Okay, now the amount of gravitational field that is exerted by this mass AB, okay, is given by minus G dm cos alpha by S square. Okay, and we saw this last time. So just to refresh your memory, remember we had this small two-dimensional ring now, okay, and we said that this will exert some gravitational field at point P, and when we decompose the components, we have two components here, right? We have the one coming from this top mass here, so that we labeled as G1, okay, and the field that was coming from this bottom mass was G2, and we said that we can decompose in x and y directions, and the y components will cancel, and all you're left with is this component along the x-axis. So this is our x-axis, and so we get some factor of G times cosine of alpha, which is this term right here. Okay, so that's how we got this expression that the field that is exerted by the ring is just minus G times m times cos alpha divided by s square, right? S is the distance between this mass element and p. Okay, and we integrate this small mass element now to get the entire mass of the ring. Okay, now all we are doing is we are saying let's take this mass m now of this ring to be dm. Okay, so that is now mass dm for our case for our spherical shell. So this entire mass of ab, okay, will be dm, and so if that is the value dm, then this is what you're integrating now. Okay, and so you are getting the entire mass of the spherical shell. Okay, now again from using the trigonometric concepts, we had done this before as well. Remember this radius of your slice here, as you can see, will be r sine theta, right? Sine theta is opposite side by hypotenuse, so this side, this radius of this ring is r sine theta. Okay, now if I look from the side view, this is what I'm seeing, right? R sine theta is this value, r is the value of the distance from the from your value uh, of the center of the of your of a spherical shell. So we are looking at from the side view, the center and the actual width here looks the same. Okay, and from here what we know is that this width of this arc here is r times d theta. Okay, which is this small angle here. Okay, so our total area that we are looking at for our ring will be this 2 pi r sine theta, okay, times this width, which is r d theta. Okay, so we have done this before, it's exactly the same expression. Okay, and we are using the idea that sigma is the surface density, so dm can be written as sigma times this value here, 2 pi r sine theta, and that's what we have written down. Okay, and so from here you get the value for dm as m by 2, because you have this pi and pi will cancel. Okay, r square and r square will cancel, so you have a 2 left when you cancel 2 here, so there will be a 2 left, so you get m by 2 sine theta d theta, and that is your expression for dm. Okay, so we want to plug that in now. So for your field now, this is what you're integrating. Okay, and dm we just found out was minus gm by 2. Sorry, dm is just m by 2 sine theta d theta, and that's what we are plugging it in here. Okay, you have a cos alpha term and you have s square. Okay, so that is our expression, that is our starting point now for a spherical shell. Okay, so we have to know this expression beforehand, and the only way to do it is actually you have to calculate for the ring in the beginning. Okay, in this expression, see, we need to get rid of s square because s is related to this expression right here. Okay, so it is meaningless for us because, you know, if you consider a different slice, the value of s will change. Okay, what are the common factors that we need? This r, capital R, is the radius of the spherical shell, so we want to express everything in terms of this capital R. Okay, and the second thing that we are worried about is where this point P is located. So the way we have chosen the axis, as we increase or decrease the value of this small r, our value of point P will change, right? So if I increase the value of r, it will go further away. If I decrease the value of this small r, then this P point can even come inside my spherical shell. Okay, so what I want to do is I want to get rid of this s, and I want to get rid of this alpha as well, right? So those are meaningless variables for me. Okay, so that is what I intend to do here. So this is our expression of what we are getting. We have this center point origin of our spherical shell, r is the radius. Okay, this is the slice radius that we were seeing, r sine theta. We have defined s and this small r. Okay, so now the typical strategy is to use the law of cosines. Okay, and what is the law of cosines? It says that suppose I want to find the value of this side s. Okay, so square of this side, s square, will be the square of the other two sides, r square, small r square, plus capital R square, minus 2 times this small r times capital R times the angle that is opposite to the side, which is this cos theta. Okay, so that is the law of cosines. It is valid for all the triangles. So here that is the expression we are going to use. And from here, what we are going to do is we are going to write and take a derivative so that we can get rid of this value of d theta. Okay, so if I take the derivative, I get 2s ds on the left hand side. Okay, and remember r and this capital R, they are constant terms. So for questioning right now, I can just take the derivative and it will be 0. So whatever I get is I get the last term remaining, which is minus 2 small r capital R. And when I take the derivative of cos of the angle, I get minus of sine angle d theta, and minus will become plus. So I get sine theta d theta will be s by small r capital R times ds. Okay, so that is my one expression. I'm getting rid of sine theta d theta. Okay, and again, the reason why we have to get rid of this is because they are related to each other. Okay, so you cannot just assume that they are constants and take it out of the integration. That is not a logical way to do it. You see, because sine theta d theta is related to ds. Okay, so these two terms are related to each other. Okay, so that is our first expression. So we can get rid of sine theta d theta. And second expression is in terms of cos of alpha. So if I want to get rid of cos of alpha, again I can use the law of cosines. So I want this value, so cosine of this value. So I will get capital R square will be small r square plus s square minus 2rs times this value cos of alpha. Okay, so that is another law of cosines. Okay, and from here I get the value of cosine alpha. Cosine alpha will be r square plus s square minus r square, and you have to take this term on the other side, right? So you get cos alpha becomes positive, and then I have to divide by 2rs. Okay, so that is my expression. So now you have sine theta d theta and you have cos alpha. All we have to do is we have to plug that in here. So I get minus gm by 2 as my expression. It is already there. For sine theta d theta, I'm writing s by r times ds, and I have 1 over s square, that is already there. So I've written 1 over s square here, and then cos of alpha is this expression right here, r square plus s square minus r square divided by 2rs. Okay, so now I can do some simplification. S and s will cancel. Okay, and I guess that's about it. You have minus gm by 2 times 2 will become 4. I have a s square term and I have a r square term and I have a capital R. So that's in my denominator. Okay, and in the numerator I have s square plus r square minus capital R square times ds. Okay, so that is what my expression is. So here I can take the small s square inside, and so I get an expression like this: minus gm by 4r square capital R 1 plus r square minus r square by s square ds. And see, now what we have done here, now we have this expression. Now in terms of g is a constant, capital M is constant, r is constant, r is capital R is constant. So all we are doing is we are integrating with respect to ds now. Okay, and so we'll get rid of this ds variable, and all the expressions will be in terms of small r and capital R. Okay, and that is what we intend to do. So we have to now see our limits of integration. Okay, so our limits of integration basically is varying from this theta, right? So we are going from theta from this point all the way, so that is 0, right? So if I consider a small slice here in the beginning, so this theta is almost 0, and then if I consider the last slice on this end, then theta will go all the way to pi. Okay, and that is my integration limits. So that's what I want to do. For theta is equal to 0, I can plug it into this expression of law of cosines here, and I'm getting that s square will be r square plus r capital R square minus 2rr, right? So that is for the first time when theta is 0. So I get s is equal to r minus r. Okay, small r minus capital R when theta is 0. Similarly, when theta is pi, I will get a minus sign here. So my entire expression becomes a positive term. So I get s is equal to r plus r. So those are my integration limits. See, so now I can get rid of this little s which is in my integration. Okay, so that's what I want to do. I want to integrate this now. So I have a g, so I want to integrate it from r minus r to r plus r. Okay, and I have the expression minus gm by 4r square capital R, and the expression was 1 plus r square minus capital R square divided by s square times ds. Okay, so again all these terms are now constants, so now they can come out. So there you go, the integration becomes very easy. First term is just 1, so I get just s, and I have to apply the limits r minus r to r plus r. Second expression, again r square minus r square is constant, so it just stays as it is. I have 1 over s square, so that is s raised to minus 2. So I'm integrating x raised to n, so I get x raised to n plus 1 divided by n plus 1. That is my integration of this term. So I get s raised to minus 2 plus 1 divided by minus 2 plus 1, which is minus 1. Okay, so for the first term, I have r plus r minus of this expression. So I get minus r and minus, so I get plus r. Okay, so now I will have r and r will get cancelled. So I will be left with 2 capital R. Okay, now let's look at the second term. I have minus sign here, so I get a minus, and r square minus r square is already there, it's constant. So here I have basically s raised to minus 2 plus 1, so that is 1 over s. So I get 1 plus first term r plus r minus 1 divided by r minus r. Okay, and so I just have to take the LCM. So if I take the LCM, in the denominator I get r square minus r square, and so now you can cancel these terms here. Okay, they are the same, and on the numerator I'll get r minus r as the first term minus of r plus r. So if I take the minus inside, I get minus r and minus r. Okay, so r minus r is 0 and minus r, and then I have a minus r. So I have minus of 2 of r. Okay, and minus of 2 of r will be plus 2 of r. Okay, so now I have 4r here. Okay, so I have a 4r in the denominator as well. So 4r and 4r will get cancelled. So I am left with minus gm by r square, and there is a unit vector I showing that it is in that x direction, and that is my expression. After all the math and all the integration, you finally get that the value of g is again the simplified expression minus g times total mass divided by r square for the value of r being greater than your capital R. That means when you are outside the spherical shell, you are getting the expression is looking like this, and this simply means that this spherical shell is behaving like a point mass of mass capital M, and r is just the distance of separation. So what happens inside the spherical shell? So if you are going inside the spherical shell, that means the small r here at any given point will be smaller than the capital R. That means our limits of integration here have to be changed. Okay, so the limits of integration will become capital R minus R to capital R plus R. Okay, so that is how we have to change the limits. Okay, and the expression remains the same. We have minus gm by 4 small r square r, and then you have this expression 1 plus this expression right here. Okay, again we will be integrating. These all terms are constant, they will come out, and so you're integrating these parts. Again you get the same value of s, and the integration limits are r minus r to r plus r, and even the second expression is the same. Okay, so here again you have r plus r minus of r, and minus r becomes plus r. So now you are getting rid of this capital R, you see. So you are left with 2r, which is a small r. Okay, and in this second here expression here, when you integrate it, again you have minus term here, it comes out because of the 1 over s. So you have minus term, r square minus r square is there, and now you have 1 plus r plus capital R minus 1 divided by r minus r. Okay, so again we are taking the LCM, so this expression will get cancelled, and you have r square minus r square, but here you have opposite of that, you have capital R square minus small r square, so this minus sign will get cancelled as well. Okay, and inside this LCM you have r minus r, that is your first term, and you have a minus, and you have r plus r, so you have minus r minus r. Okay, so again capital R will get cancelled, and you are getting minus 2 of small r. Okay, there you go. So you have plus 2r and minus 2 of r, so you are getting the value now as 0. Okay, and so that is something that is very non-intuitive. You couldn't have predicted this just by thinking about the system. Okay, so what we are getting is that the gravitational field inside a spherical shell, okay, is actually 0. Okay, so any mass that you put inside a spherical shell, it won't feel any gravitational force acting on it. Okay, we can summarize for the case of spherical shell that we are getting the first case for outside the shell as minus gm by r square, right? And here the spherical shell acts like a point mass. However, if you go inside the shell, we are getting that the gravitational field is 0. Okay. So from this gravitational field idea, what we can do is we can relate the value to potential of a spherical shell. Okay, now the gravitational potential that we have looked, right, which is just the amount of work done to move a mass to certain point where we are considering the field to exist, right, is given by this expression minus g times m by r. So now when we try to find the gravitational potential, just like the gravitational field, we have to integrate with this expression. Okay, so g and r will be the same, but you have to integrate this mass. Okay, and that's what we will be doing. Okay, so again the idea is very similar. You will take the shell, you will take a slice, you will get all your trigonometry right, and again the only thing, the difference is your expression will be minus g dm divided by r. Okay, so that is what you will be doing. Okay, so minus g dm by r, and when you integrate this you will get the entire volume. Okay, again strategy is the same. Use the law of cosines, get an expression. This is your expression that you get, and then you try to integrate this expression. Okay, and once you integrate this expression, um, again here what you're getting is 2 pi capital R, they are constant. Sigma is the surface mass density, that is constant, it comes out. G is constant, even small r is constant. Okay, the only thing that is inside is dx, and once you solve this you get this expression that v is minus mg by r. Okay, so again the gravitational potential of a spherical shell is again this value outside the shell. Okay, and it is as if the entire mass of the spherical shell acts at a small from the small origin point. Okay, so you can concentrate the entire shell to just a point. Okay, that's the idea. Okay, however, if you look at the surface of the shell, okay, then you have to look at the integration limits. Okay, so this integration limits at the surface, r will be equal to r. Okay, so the first expression here becomes 0, and r plus r, since small r is equal to this capital R. Okay, at the surface you get 0 to 2r as the integration limits. Okay, see this r at the surface will be equal to this capital R. Okay, so here you have to plug in those integration limits. Okay, your expression remains the same. All right, and if you calculate it, you will get minus mg by capital R. You see the r now has become the radius of the spherical shell. Okay, so that is the potential at the surface of a shell. Okay, or for a matter of fact it could be a hollow planet. Okay, so what happens interestingly inside the shell? Okay, so again the integration limits will change just like before. You will solve it and you will find that the value is minus mg by r. Okay, and that is exactly the same value that you're getting at the surface. Okay, so to summarize for the potential of the spherical shell, what we are getting is that outside the spherical shell we are getting v is minus mg by r, so it just acts like a point mass. At the surface it is minus mg by capital R, that is the radius of the shell. Okay, I should write that down. R is the radius of the shell, and inside the value is the same. Okay, that means the gravitational potential inside the shell and at the surface is the same. So you see, the gravitational potential is not zero, it is the same. It is the gravitational field that is zero inside, because the gravitational potential doesn't vary. Okay, let me tell you something about the relationship between the gravitational potential and the gravitational field. Okay, so the gravitational field, typically, if you look in your textbooks, is given as E, is just the negative gradient of a potential. Okay, we have already seen this expression. Okay, that the field, okay, conservative field is negative gradient of the potential. Remember from unit 1. Okay, and it is the same idea here. So if I know that the potential of a spherical shell is this outside the shell, minus mg by r. Okay, so what I can do is I can take the gradient of this potential, and that should give me the value for gravitational field. So if I take the derivative of this function minus mg by r, I'm getting E is minus mg by r square, and that is my expression for the gravitational field if I know what is the potential of the field at a certain location. Okay, so outside the shell, I am saying that if I take the derivative, if I look at the change, then I get minus mg by r square, and that is the expression that I should be getting. Okay, and it makes sense as well. If you go inside the shell, your potential V is actually constant. So minus mg by r, capital R, is a constant term. So when I take the derivative of this, I will actually get 0, and that is what is the field that is inside the shell. Okay, I just take the derivative of the potential. Potential is constant at the surface and inside. It is just this value minus mg by capital R, and so my value for E, which is the gravitational field inside the shell, should be 0. Okay, gravitational potential and gravitational field that is created by a solid sphere. So here now I am going to present exactly the same approach that we were discussing just now, that I will find the gravitational potential first, and from here I will find the gravitational field. Okay, we have to first consider a small mass element, and then we have to go and create our entire solid sphere. Okay, so what we are going to do is we are going to first find the gravitational potential at a point outside the solid sphere. Okay, now we have the volume of the sphere is 4 by 3 pi capital R cube. R, capital R, is the radius of this solid sphere, and now what we are going to say is that let's imagine that this sphere is made of some hollow spherical shells. Okay, so let's consider the first spherical shell, which is right here. Okay, so in this spherical shell, if I consider a spherical shell here, I know that the gravitational potential due to the spherical shell is just minus g times mass of the shell times r. Okay, so if I go to the next shell, I will get minus g, the mass of the next shell, divided by r. And then I can keep going and keep creating all these concentric shells and go to the final radius of capital R. Okay, so what that means is my total gravitational potential from all these concentric shells will actually add up. So I'll get minus g by r, and I can add all the masses, and I will get V outside of this solid sphere will just be minus gm by small r. Okay, remember, point P is outside the shell. Okay, so that is just a fast way of visualizing the problem, right? You already know what is the gravitational potential due to a spherical shell outside the shell, and so you use this idea. You create as many shells as you can inside this solid sphere, and all those gravitational fields just add up, and you get the entire gravitational field that is created by a solid sphere. And so the potential there at that point where the field is existing is minus g m by r. Okay, so from just this relationship we can understand that at the surface, when r will be capital R, I will just get minus g m by r at the surface. Okay, so two things are straightforward: what is outside and what is at the surface. The tricky part again lies what is inside the solid sphere. Let's look at the potential inside the solid sphere. Okay, so what we are going to do is we are going to consider some radius r. Okay, this small r, and we are going to say that we can divide now the solid sphere into two components. One having a solid sphere of this area bounded by the region up to R, and then there will be a concentric shell that will emerge from this remaining mass of the solid sphere. Okay, so to find the potential at any point P at this position R, we can find the value of potential that is arising from the inner solid sphere, and we can find the value from the spherical shell. Okay, and again we have to use the idea of the density as being the constant mass over volume. Okay, so let capital R be the complete radius of this solid sphere. Okay, so what we can do is we know that from our previous discussion that the value for the inner solid sphere, okay, is essentially your g mass of the sphere divided by r. Okay, and here we know that density is mass over volume. So for mass we can write in terms of density as 4 by 3 pi r cube times density function, and you have your g over r. Okay, so that is your expression that is coming for the potential from the inner solid sphere at the surface of the sphere of radius small r. Okay, and now we are left with the spherical shell, that is this region outside this value of r. Okay, so ranging from r to capital R. So we already know what the expression is for the spherical shell as well. Okay, and for the spherical shell, again we have to take into account that we can use the idea of concentric shells and we can integrate the volume. So we will have some volume of 4 pi x square, and then we are going to change the x from all the way from small r to capital R, and when we integrate this volume, we will get the entire volume of this thick shell that is creating the potential. Okay, so here we can plug in this expression of again your value of g by r. Okay, so instead of r we have x now because it's a variable, it is changing, and then we have your density times the volume. Okay, so we have again the volume is 4 pi x square dx. Okay, so now we can try to integrate this function. Okay, so you have 4 pi rho and g, these are constants, they can come outside, and you have x dx, so that is just x square by 2, which is if you substitute the end limits, we'll get capital R square minus small r square divided by 2. Okay, and here now what we can do is we can divide and multiply this equation by 3, and it will be apparent why we are trying to do this. Okay, so if you look at our total expression now, it is our first term from the solid sphere, which is 4 by 3 pi rho g r square, and then you have a second expression now, which is 4 by 3 pi rho g, and there is some other expression inside. Okay, so we have a common factor of 4 by 3 pi rho g, which we can take outside, and then in the inner expression we can add these terms. So you have capital 3r square by 2, and you have a minus 3r square, and you have a plus r square, and this is 3 halves. So when you add them, you will get 1 half. Okay, so you get this expression right here. All right, and in this expression we know what the value of rho is. Okay, so rho is just the mass by the entire volume. Okay, so if we plug in that value, we are 4 by 3 pi l2 will get cancelled, and you're left with your potential term as being minus m times this expression 3r square minus r square divided by this 2r cube times your g. Okay, so that is the potential from the solid sphere inside the solid sphere. Okay. And so here you can see that if I take the point P at the center of the sphere, that means this small r is 0. So then my potential becomes minus m 3 capital R square divided by 2 r cube times this g. So I have a value of 3 halves times the value mg by r, which is the value of the potential at the surface. So the gravitational potential at the center of the solid sphere is actually equal to 1/2 times the gravitational potential
at its surface. Okay, so that is a very non-intuitive result. All right, so we can continue along these lines and try to now get the values for the gravitational field of the solid sphere, because now we know the values of the potential. So again, outside the solid sphere, we know that the potential is minus gm divided by little r. So we can take the gradient of this function, and if I take the negative gradient, I am getting minus gm by r square. Okay, and that is the gravitational field uh, outside the solid sphere. Okay, so again, it is a approximation that this gravitational field is as if the entire mass of the solid sphere is concentrated at its center. Okay, and generalizing from this result, if I want the gravitational field at the surface of the solid sphere, then this little r will become my capital R, which is the radius of the sphere, and my value becomes minus mg by capital R square. Okay, and again, I can go inside my solid sphere now, and I have the function of the potential which is present inside my solid sphere, which is this value right here. So if I take the negative gradient, then I'm seeing that since this capital R is constant, I lose this term and I'm left only with this R square term here. And if I take the derivative, I will get 2R, and I have the expression minus mg by 2R cube, capital R cube. And so I get a function minus mg by R cube times R. And essentially, for my problem, mg and capital R is constant. So my gravitational field is proportional to R. And I can visualize this field. If I plot the gravitational field versus R, I can see that inside the sphere, I'm getting a linear relationship. Okay, whereas outside the sphere, my gravitational field is actually proportional to 1 over r square, and it dies down as r increases and goes to infinity.